Hello and welcome back. In this video we're going to look at the factors that affect the hydration and lattice enthalpies. With our ionic compounds we find we have a range of melting and boiling points, but why might that be? Well, it's all to do with the value of the lattice enthalpy and the factors that might affect it. At one end of the scale we've got magnesium oxide with a melting point of 2880 degrees C, the highest melting point of any ionic solid. And at the other end of the scale we have 1-ethyl-3-methyl-imidazolium chloride. Now that is liquid at room temperature, an ionic liquid in fact. So what factors make one of these chemicals different from the other? Another thing that changes from one ionic compound to another is its solubility in water. What causes it to be different in solubility from other chemicals really does depend on the lattice enthalpy and the enthalpy of hydration. So here we have two ends of the scale. We have cesium hydroxide is the most soluble ionic compound, and you can see it looks a bit mushy. That's because it's so soluble it will actually draw moisture from the air. It is deliquescent. In fact, this property is hygroscopic. And so basically it's very difficult to form crystals apart from in a completely moisture-free environment. At the other end of the scale, barium sulfate is the least soluble ionic compound. It just won't dissolve. It just won't. And so it is the opposite. It is efflorescent. It actually dries out in air. And we have some chemicals that are like this, that are basically they dry out. But what about desiccants? What about like silicon dioxide? Well, they're actually deliquescent, right? The silica gel packets that you get, because what happens is they absorb moisture from the air and themselves become more liquid. So the actual air gets less moisture filled. So those little sachets you find in packets of shoes to keep them dry and etc., they are deliquescent chemicals. Now, the lattice enthalpy is connected to the ion size, remembering that the ion gets larger as you get to a heavier element further down on the periodic table, for example. As a larger ion is considered, the energy required to form 1 mole of the lattice becomes less, which means that the lattice enthalpy generally becomes less negative as you go down. So if you look at the table just there, we've got lithium chloride with a tiny little lithium, and it goes down to larger and larger and larger ions. Notice that the lattice enthalpy is going from -800 up to -600. It is becoming less negative. It is taking less energy required to form 1 mole of the lattice. But notice what's happening with the melting points on that right-hand side. If we just strike through lithium for a second, and we'll come back to that, sodium chloride has a high melting point when the ion is quite small, and it goes to a lower melting point when the ion is quite large. This is because of the lattice enthalpy, because the amount of energy required to form 1 mole of the lattice, it basically means that something that requires a large amount of energy to form a lattice is also going to require a large amount of energy to break that lattice again. And so therefore, when the lattice enthalpy is high, so is the melting point, which means the smaller ions tend to have the higher melting point in connection to the lattice enthalpy. Lithium chloride, though, doesn't fit that pattern. Even though it does fit the pattern in terms of lattice enthalpy, it doesn't fit the pattern in terms of melting point. And this is because it is so small that its behavior starts to diverge away from this typical ionic bonding behavior. It starts to behave more like a covalent compound. There's something out there called Phagen's rules that say that small, highly charged cations polarize large anions, inducing partial covalent character. Now, that change means that it will actually melt much early on at a lower temperature. That was size. Let's talk about charge. Well, as ionic charge increases, the attraction between ions increase. There's going to be greater electrostatic attraction, and that means there's going to be a greater force holding together the particular ions. It means it's going to take greater energy to separate them. You gain more energy in formation, and you have to put in more energy to separate them again. So the lattice enthalpy becomes more negative as we go to greater ionic charge. Look at the table. So look at the sodium, for example, the Na+. So first of all, we've got NaCl, salt. Lattice enthalpy is -788. But when we go to sodium oxide, we've got Na2O. Yes, we have got the Na, but we've got two of them now. So there's more charge involved. It's going to be held together with even more force. And so therefore, it's going to take greater energy to separate and break that lattice down once more. With calcium oxide, it has got a charge of +2, so the lattice enthalpy is really very large and negative. It takes an awful lot of energy to break calcium oxide. Now, magnesium oxide, it also has a +2, but it has a size advantage on the calcium. It is slightly smaller, so you get an interplay of both phenomena. And then if we look at how that affects the melting point, again, this lattice enthalpy is connected to the melting point, because those things that require a huge amount of energy to break the lattice also have a very high melting point. That is why the melting point is both dependent on the size of the ion and the charge on the ion. Aluminium oxide, when it is in its ionic crystalline formation, Al2O3, enjoys being a small ion with a large charge, and so therefore we have exceptionally high lattice enthalpies. Not only high lattice enthalpies, very, very large melting point. And as a side note, these aluminium oxides, when it is just by itself, is the gemstone sapphire, which is the one in the middle there, the blue one. And then with slight impurities, with a small amount of chromium in there, we have it turn red, and that is ruby. And if we add a little bit of zirconium, silicon oxide, a very similar chemical, then what we get is zircon, a different crystal there. But they all have this thing in common, that they have small ions, large charge, and therefore they have a very large melting point. Let's take a look at how this looks on a periodic table. So if you imagine a cation Na+, which would be sort of top left in this diagram. Now what we remember is that the lattice energy increases as the ion gets smaller. So basically, sodium at the top there has the largest lattice enthalpy than the things down below it. And this results in things like the melting point basically getting smaller as you go down the periodic table. But as we go to the right, and if we're talking about cations, we talk about group 2 would have 2+, and group 3 would have 3+. As we go to greater and greater charges, then the lattice enthalpy will also increase to the right. So technically the top right is the place where we'd find the largest enthalpies, lattice enthalpies, and the bottom left the smallest. So the top right would also therefore have the highest melting point, the bottom left the smallest melting point. This same situation is mirrored when we talk about enthalpy of hydration in the energy stored up in the dissolving of a substance. It's affected by both ionic size and ionic charge. As the ionic radius increases, as you go down the periodic table, that what we find is the attraction between the ion and the water molecule, which enables it to be soluble and dissolve in the first place, it decreases because the attraction is less. The hydration enthalpy becomes less negative, so it becomes a smaller value. And that means that as we go down the periodic table, the enthalpy of hydration gets smaller. Now, what about going from left to right as we go across the different groups? Well, as the ionic charge increases, then the attraction with water molecules increases. So the further we are, the more charge we have on that cation, then the greater the hydration enthalpy. Understanding these two values, the lattice enthalpy and the hydration enthalpy, enable us to make predictions about the solubility of the substance. If the lattice enthalpy is equal to or greater than the sum of the hydration enthalpies, then more energy is required to break the lattice than is released from that hydration. So the overall enthalpy change of solution will become positive, it will be endothermic. It means the process absorbs energy from the surroundings. It's not energetically favourable to happen unless there is a strong entropy gain that makes the overall Gibbs free energy negative. Don't worry about that. basically what we can say is it will not dissolve easily, but it will be much more soluble if the lattice enthalpy is much smaller than the sum of the hydration enthalpies. So if we take a look at the table just here, that we can see where they are similar to each other in value. The lattice enthalpy of sodium chloride is similar to the hydration enthalpy, but it is still smaller. Then we find the solubility is about 36. If we look at the calcium chloride, we can see that the value of the lattice enthalpy is significantly smaller than the hydration enthalpy. It is going to be more soluble in water. And so how the solubility is measured is the grams of this substance per 100 grams of water. And you can see that we've almost got as many grams of calcium chloride in water as there is water in water. It will hold far more. It is far more soluble. And that is predictable just by comparing the two enthalpies.